So in the talk today, I have 4 sections: introduction about Apache Samza, and then a deep dive of our portable runner, and then more importantly, I chatted with a couple of folks. You guys are very interested in our use cases, so I will spend some time there. And then lastly, quickly talk about future work. And actually, just a couple months ago, my co-worker Xingyu just did a talk for Samza Runner for Bing in Berlin. So for this one, I'm not going to repeat like 100% what he has already covered. Instead, I will do this kind of like a sliding window, cover a little bit of what he has already talked about. And then I'll definitely add new materials there as well. So just to set up the context, Apache Samza, so you have heard about all kinds of runners for Bing. There are Flame Runner, there are Spark Runner, there are Flow Runners. So what is so special about Samza? So Samza was developed at LinkedIn a couple of years ago in 2013, and it became the top-level Apache project since late 2014. And we have a bunch of users for Apache Samza, LinkedIn definitely being one of the heavy users. And there are other companies, especially like Intuit, for example, they not only use Apache Samza, they also use Apache Bing on top of Samza Runner. So they're actually writing Bing pipeline on Samza. And to summarize, Samza is a distributed stream processing framework for building stateless or stateful applications. And I also want to emphasize that we are a streaming engine at scale, because that's really the thing that I think makes Samza stand out. And what kind of scale are we talking about? At LinkedIn, we're processing over 1.5 trillion messages per day. And today there are more than 3,000 jobs running in production. So this is the kind of scale that we are handling. So it's a lot of jobs, a lot of messages to process. And it's not just about scalability. We also make sure that this is a highly available service. Right? You cannot just have a lot of job and then they break every single day or something. That's not the way to run business. We have 99.99 availability, especially for running Samza on Yang. So so how do we achieve this high availability and how do we operate at scale? So first of all, it's very basic to enable. So first of all, Samza is running on Yang for many of the use cases. So it's very basic to enable HA on Yang, high availability for the RM. In additionally, we have incremental checkpointing in Samza. That's one of the unique functionality feature that we have. So when we do checkpointing, instead of like flushing out the entire state to some remote place like HDFS or something, we do incremental checkpointing. We just the small state change and offset change locally to RocksDB, and then this got further persisted to Kafka, just in case we lose the host locally. And because we persist the state locally in RocksDB, it's important to have this thing called host affinity, so that when you redeploy your job or when you shut down and restart, we try to allocate the Yang container to the exact same host that your job previously was running, so that instead of restoring your states from Kafka or remotely, you already have your state locally in the same disk. So this will make the recover time super fast. But in the failure of host affinity, right? Like for example, even if you lose the entire host, the host is broken, you have to restore the states from Kafka. But before that, we still have another feature called standby container. So what it does is we actually have a shadow container in addition to the actual running containers. This shadow container also reads the same input, perform the same operation, and write to the same states. So in this case, whenever you lose host affinity, you lose your container, we can still start a standby container, and then that's how you can continue your processing with a minimal downtime. So this is how Samza is able to operating at a very large scale by doing this. In addition to large scale in terms of messages to process, number of jobs, we are also, when I talk about scale, it's also about complexity of use cases. Right? So this slide is our stream processing ecosystem at LinkedIn. As you can see, for Samza, we interact with lots of external systems, including, so we are heavy users of Kafka, by the way. Anything that can be captured, we capture them in Kafka. We actually, as I mentioned, we process 1.5 trillion messages per day in Samza, and Kafka itself handles 5 trillion messages every day for LinkedIn. And then, aside from Kafka, we also have a system called Brooklyn, which was recently open source. It's very nice. It does change capture for database like Oracle, MySQL. And at LinkedIn, we use our main database as Espresso. It's an internal in-house database. We capture the change from database, and then from Brooklyn, we can also read from Brooklyn to do stream processing. And for the results of the stream processing, we can either write back to the main database or OLTP databases, or we can write to a bunch of other external systems, including like Couchbase as a cache service, or HDFS for offline processing. Pinot, we just have a talk yesterday. It's a really cool Apache project. It's a kind of like an OLAP data store. You can also check it out. So this is the complexity of our stream processing system. It interacts with different systems, and then it has all kinds of combinations, like read from Kafka, write to some store, or read from Kafka, join with a certain store, and then write back to Kafka. All these combinations are there. So this is like, this is how complicated our ecosystem is. And about 2 years ago, we developed Samza Runner for Bing. This turns out to be a great win, a great success. So on one hand, we have Samza as the streaming engine, which can really handle really very large scale in terms of stream processing. It does really well in terms of big stateful job, right? For example, there was a couple stateful job at LinkedIn that use, I think, more than 1 terabyte of states. So this is very massive and very intimidating. So on one hand, we have this great streaming engine. On the other hand, we have Apache Beam, which has state-of-art data processing API and model. And more importantly, as I'll talk in this in this talk today, is the language portability framework that got support from Bing, right? Because now with Bing, we can do stream processing beyond Java, including Python, Golang, and all of them. Also, there are like C code support and all these open source I/O components and like all kinds of libraries that are available on Bing. These are really great. So that's pretty much about the context. I only highlight a few points. If you want to know more details, definitely check out the previous talk by my colleague Xingyu. So next, I would start talking about Samza Portable Runner. So first of all, why bother doing this? Right? This actually doesn't come as free, because we really have to build a portable runner, even though we already have a Samza Java runner. So turns out there's a strong business motivation behind this. So as the stream infrastructure team at LinkedIn, we are a strong believer of stream processing in general. We really think that it's very critical to make stream processing available everywhere beyond Java. I think one of the slides that mentioned today that a lot of the big data systems are only available in Java. Right? That's not great. At LinkedIn Java is the main language being used, but Python, for example, is the second most popular language being used. So a lot of the internal projects built at LinkedIn are using Python. So it's a shame that they cannot use stream processing because their language preference. And in addition, we investing a lot in machine learning. And as you know, machine learning, in the area of machine learning, Python is the dominant language. So by enabling stream processing in Python, we can really support abundance of machine learning use cases. And potentially, we actually have one team at LinkedIn who wants to use Golang for stream processing. That's interesting. But because there's the single use case there, and we haven't had the resource to build it for them. I think we did try to prototype this, and it did work, which is very impressive, but we just don't have time to productionize this yet. So from from very high level, as you probably know about this by attending to different portability talks already, but just from a Samza runner's perspective, the way that portable runner works is that users will compose pipelines using different kinds of language SDK. They can use Java SDK, Python SDK. These SDKs, once composed a pipeline, they got translated into a language-independent pipeline written in Perl buffer. That is the runner API that many of you may already know about. And this Beam pipeline got eventually submitted and executed in Samza runner. So that's just a high-level idea how portability works. And how exactly we translate those Beam pipeline into Samza. So there are many P transforms in Beam, but turns out there are only a few of them that are fundamental. You can reduce many of the P transforms into a couple of them, including Padu, group by key, and I/O as well. So for us, we translate I/O into system consumer or system producer for Samza. So system consumer and producer are the I/O components for Samza. Also, in addition, we also do watermark generation in the system consumer, and then the watermark got populated throughout the entire pipeline. For Padu, we use we have simple do function runner and executable do function runner. The executable do function runner is for Python. This one will actually make the call to Python SDK worker. And for Windows, that's trivial. And for group by key, again, we do this group by key by using the partition by and other high-level API in Samza. So essentially, the Beam pipeline got translated into a Samza DAG, and then we run this Samza DAG in the Samza cluster. So one thing I want to mention is that we try to share as much code as possible for the legacy or the Java runner and the Python runner. So this turns out to be very productive and very helpful in the end. So I already covered this. In order to translate the pipeline to portable runner, we do things like executable stage, flatten, group by. We also do a bunch of work for I/O. Why is that? You probably know that Beam itself has a lot of I/Os already, especially in both Java and in Python. So why are we still doing a lot of I/O work? So the reason is that at LinkedIn, we actually do not use Python I/O. As I mentioned before, Java is the main language that is being used at LinkedIn. So a lot of the clients and components are written in Java, and they are not really available in Python. This, by the way, predates the cross-language work. That's why we have to build some customized solution. And even for Kafka, right? I mean, you probably know that there is some Python Kafka library which you can use, but still we don't use that because at LinkedIn we have a more customized version of Kafka that has supports like large message support, like encryption and all the other features. So for that reasons, we actually want to have a convergence story there, not to use like Python IO directly. And another reason is that it's probably more efficient to do IOs on the Java side anyway, because Python is not known to be super efficient in terms of performance. So for this reason, we actually translate the Python IO into a Java IO. So this is an example pipeline how users would write Bing Python job. So they will say that after creating a pipeline, they will just say read from Kafka, and then specifying the cluster and the topic. So why cluster here? Because we are heavy users of Kafka, so we actually run multiple, actually a dozen of Kafka clusters. So all of them have a name, and we have pre-generated configs so that in order to talk to a certain Kafka cluster, you only need to provide a name. So we hide those broker address and zookeeper address, all these details under the hood. So this is what a Python users would write a pipeline. Simply say what cluster they want to read from and which topic they want to read from. And the rest of them are just standard Bing pipeline, like doing mapping, doing window, doing group by key. At the end of this, they could just say write to Kafka, and then that's it. So from the Python user's perspective, it's almost like they're doing everything in Python. They don't even know that there's a Java process behind, there's a Java Kafka client behind the scene. A little bit more details how we did that. Basically, we translate the portable pipeline into defining some portal buffer there to define the p-transform. As you see, this p-transform has information about the cluster name, the topic name. Also, it could contain additional information of the configs if users want to specify them. And then under the hood, because the pipeline got submitted to the Java side, Java has all this information to construct the real Java Kafka client. And then the pipeline is good to go and good to run. So beyond I/O, like Kafka I/O and other I/O, we also have very interesting feature in Samza that's called Table API. It's a little bit, it's more like an extension to I/O. It could contain like local table or remote table. For remote table, for example, it could be Couchbase. It could be all the other databases that I have mentioned. The reason we want to provide this layer, this API, this feature, is that this makes things easy for people to do things like string table join. Right? It's possible that you just read from the string and then you write a Pardue, and inside this Pardue you invoke your Couchbase library or some MySQL library to do this string table join yourself. But it's much more convenient if we already provide a layer of table API, and people can simply just do a string table join with one p-transform. And also with this table API, we provide out-of-box support for things like throttling or rate limiting, also like caching. All of these functionalities are provided at this layer, so that users don't need to worry about all of this. This is important when you have like 3,000 jobs, when you have hundreds of users with different use cases, right? If you only have a few jobs, they can always customize their job. But when you have a lot of users, it makes sense to start building this intermediate layer and just make things easier to use. And that creates a lot of value for the company. So for example, if you, as an example of using table API for write, for the Kafka input that people get, after processing, they can just apply a table write P transform. At the end, the results will be synced to a remote or local table. Probably more interesting is the table read cases where people can do string table join. Not only in Java, but also in Python. Because, again, like I said, a lot of our systems are linting are written in Java. They don't even have a Python client. So by providing this table API layer, we kind of have a standardized P transform in the Java side to interact with, say, MySQL, Couchbase, HDFS, all of this. And then in Python, we don't need to build those clients anymore. In Python, we just do the same thing as Kafka I/O, where the user will just specify that what table they want to join. And then under the hood, we translate that into Java. And then when in the runtime, only the Java client is being invoked and being used. So this is a sample code. As you can see, what people can do is they can just read from Kafka, and then with a very simple P transform to say join with Couchbase, and specifying the table name or something. And then at the next step, what you will get is basically the key, the original Kafka event, and the join event, the join results. Basically, using this key, we have lookup Couchbase, we have lookup other table. What are the results? We put them together and then return as the output of this P collection. So that's pretty much about translation. So after translation, we need to actually run this in the runtime. So when you actually execute the pipeline, right, there are parts that you can run in Java side, including I/O, states, all of this I have talked about. But there are things like UDF, like codes that people actually write in Python. So they have to be run in an SDK worker. I will not spend too much time on this because this is very standard portability framework you guys all know about. I'll talk a little bit more about Samza deployment because it's very interesting that Samza actually has a way to provide Samza as a library. In this case, we don't actually have a physical Samza cluster where that we run a lot of jobs. Instead, people just use Samza as a library, and then they deploy their application to some host that they manage themselves. And then behind the scene, we use Zookeeper for coordination, including leader election and partition assignment. So the beauty of doing this is that you can actually do rolling deployment. Instead of shutting down the entire job and then submit a new one, you can deploy your new pipeline to only, say, one of the hosts, and then you only process part of your data with your new code. This way you can kind of like test that whether your new code is working or not without affecting your entire job. Also, this also allows you to do dynamic cluster expansion. So if today, for example, we have 4 containers here, if that's not enough, you can simply throw more containers there without the need to shut down the job, resize the cluster, and then redeploy. Another way is to do deployment on YARN. This is actually common for Samza, so I don't plan to talk too much about this. For Samza Python, this is still work in progress. So after solving, we are done with translation. We know how to deploy. Next, before we actually deploy our Samza jobs to production, right? We got a problem with authentication. So at LinkedIn, we are running Samza in a multi-tenant environment, and we are not using Kubernetes or any other cluster management that has network isolation. So for us, it's possible that one sensor job can listen to data from another sensor job. In this case, if we, because you know about portability, the Java and Python has a gRPC channel to communicate data. We have to secure that channel. That's actually a requirement. So a simple solution is to enable SSL plus mutual authentication. But this could potentially introduce unnecessary overhead. So what we do instead is a very interesting solution. It's based on token and file system. So basically, as the user, the application with their own user account, start the Java process and Python process, and then by relying on file system for echo, only this application can access the token file in the file system. So in this way, we generate the token and then share the token only through file system. And then when we establish the connection from Python to Java, Java will verify that this Python process really has the correct token. If it's some unauthorized user that doesn't have the correct token, the connection will be rejected. And we also use loopback address so that this traffic does not get exposed to external network. So in order to spy on this channel, you have to log into the machine. Also, you have to have root permission. So that's how we solve this problem. It's actually very unique, very interesting. We actually put this on the pull request. Next is performance. So when we actually deploy the job to before we actually deploy the job to production, we try to test the performance, do a benchmarking of performance. Turns out the result was impressive, but in a bad way. It's like achieving like less than 100 QPS, and also with this 85 QPS, it's already saturating the single core CPU. So adding more workers will help, but it's not the final solution. So turns out what we are doing with the portability today initially is that the Java and Python is playing like a ping pong thing, where a single message is passed from Java to Python, and then Java is waiting for the response from Python. This actually significantly jack down the performance. So the key to solve this problem is bundling. Now we actually bundle or buffer a bunch of events together before waiting for the results of Python. So instead of doing a single message bouncing around, we do batches of messages bouncing around. And this theoretically could improve the performance by a lot. One more problem to solve, though, is that now because we are buffering the event, we have to persist those events. Because in Samza, we have this concept of Samza run loop, where we process one message. This message will come from the source, the I/O, all the way going through all the operations that you want to do, including repartitioning, all of that, and then finally go to the external system as the result. But if we are buffering them to wait for the results from Python, then potentially we could lose those events. So the way to handle this is to persist the events in local C, basically backed by RocksDB, and then again that got persisted to Kafka. So this way, whatever your buffer in memory is persisted. So with bundle, it helps the performance by a lot. As you can see from this chart, when there's no bundling, basically when bundle size is 1, we can only have less than 100 QPS. But by slightly doing a little bit of bundling, for example, just 20 or just 50, the performance can already go up to a couple thousand. I keep increasing the bundle size. It kind of like reached about 8,000 QPS, which is very impressive and good enough for us. And this is only for single Python worker. You can even further optimize this by adding more workers.
Did you find that it gave you bad latency? Did you also have to...
Yeah, there will be bad latency because, for example, you can only process 8,000 events per second, but your bundle size is like 50,000. That means that you are already giving like 6 seconds of latency by doing this benching. So that's why we don't actually have this large bundle size. By default, we set the bundle size to be 3,000, where you have a QPS of 4,000, and then you will have less than 1 second of delay by doing this bundling. Yeah.
One more question.
Sure.
Related with the previous slides, you had mentioned that there is SSL, no, this one, SSL and TLS thing. Why was it necessary to have that?
Because it's multiple sensor jobs could run in the same host. And then if you don't have this, and you have a plain text kind of channel, then anyone can spy on this channel.
Okay, so this is like running kind of a shared infrastructure, public infrastructure, or?
It's still internal cluster, but we have such a high bar in terms of security and authentication. Yeah.
Okay.
This is all due to GDPR, as you know.
Sorry.
And finally, I want to talk about our use cases. I think yesterday when I checked, we already have at least 10 different applications written with Samza Python or Bing Python. This one, for example, is already in production for a while and running stably. In this case, it's kind of simple where there's a machine learning team who want to use Python for OCR. Right? So OCR is basically optical character recognition. The reason they want to use Python is this library is only available in Python. I think they are using TensorFlow plus some NumPy plus some other image processing Python library. And the use case goes like I said, we are heavy user of Kafka, so everything is available in Kafka. So from Kafka, we have the image URL, which is something that, for example, user could post. If you go to LinkedIn and post something, then we have this data here. And then after getting this URL, we fetch the real picture, the real image from some internal service. And then this is then given to a TensorFlow model to extract the text from the picture. And then we just send this image URL along with the results of the OCR to another Kafka topic so that other application team can use this as their machine learning model feature or use this for other analysis, all kinds of different use cases after that. So this is a simple use case, but it kind of makes sense because this demonstrates why we want to build Samza Protocol Runner, because machine learning use case, right, they want to use Python, and they need to process Kafka data. So that's the use case. Second one is even more interesting. It's again a machine learning use case, but here we're actually doing near-line or near real-time machine learning training. What happened is that, as in many companies, LinkedIn usually do model training in offline, where you have data coming from Kafka or other places. They got ETL into HDFS. We have offline process to train the model. But the problem is that the latency could be very high. So by the time you train the model, and then you also need to push the model to online. So this latency could be a couple of hours, and sometimes it could be 1 day. But if you want to process your signal, process your data faster, that's why you want to use a streaming solution. So in this case, the team use Samza Python. They get the feature data from Kafka, they apply the window so that you get a very small batch, say 1 minute window or 2 minutes window, key by the member that they want to do the model training, and then they read from the coefficient store, which have the machine learning model that chain from offline. They read the coefficients, and then based on the new data, they update this feature, update this model, and then push back to coefficient store. So this is interesting because, for example, if you are thinking about a recommender system where you want to recommend some items to some users, or say you want to recommend some ads to some users, for the way to do it is one is you can train a global model where with all the items that you have, with all the users that you have, you train a model to kind of like predict how likely this user is going to like this item. In addition, you can have some per item model or per user model where for this specific user or this specific item, if you have enough data, you have abundant data, you can train a smaller model just for that. And this streaming pipeline helped that, because if you have a new item, a new user coming to your website, then you can really capture the data as soon as possible, and then apply that to your machine learning model, and then you can basically get a much better results from your model, instead of waiting another 5 hours or 10 hours before the offline process starts. So this, like I said, this is a very interesting use case. I think we should actually have a dedicated talk just about this, for all the backgrounds, for all the the details of the algorithm, because I'm not a machine learning expert. So I find that very interesting. So stay tuned. We will maybe in next Spring Summit we have someone to talk about this nearline training.
How long does that model take to run?
It's very fast because it's not a super complicated model. Right now, I think they're only doing this for linear model, not neural network or other things, because it's actually a recommender system. Yeah, check out generalized linear mixed model. Another use case, it's not machine learning use case, but I really like this use case, where we have a team who wants to do, who want to capture abnormal activities that happen, and then try to alert or do monitoring based on these activities. So, for example, we deploy file systems at LinkedIn to our clusters, and then these file systems, when they block a certain port or block a certain application, they will log an event to Kafka. Because again, we are having users of Kafka to do everything in Kafka. So because the data is available in Kafka, they then build a Samza Python job to read the events from Kafka, extract the key, add the timestamp, and what they want to do is they want to calculate how many blocks have happened, how many denies have happened for this specific port or this specific application in the past 1 minute window. And they want to say that if this passed some certain threshold, they want to alert some engineers, or they want to signal this to some monitoring system. So after reading from Kafka, extracting the key, adding the timestamp, however, you have to do event time processing, because otherwise, if this job is done for 3 hours, and then when you come back, then you all of a sudden process lots of data, and then your result would be wrong, right? Because if you're using processing time window, then all of a sudden you have the wrong count that you want to calculate. So by using event time event, and then apply 1 minute fixed window, and then do a combiner, basically count per key, then you just quickly get the result for the count per window per key. This is very useful. This is a pattern for different kinds of use case. I only mentioned firewall as one use case. So this is interesting because I think essentially you can write this in Java as well. No difference. And Java is the main language that is being used at LinkedIn. But still the team preferred to use Python, and it shows that actually many people just love Python. And if you make stream processing available in Python, if you build some tool available in Python, many people are just willing to use them. Also, we actually found a bug with the count per key. It didn't work initially because there was some bug in the window assigning in the Python SDK work for being open source. Took me a while to debug this, and then now the fix is merged. I think no one else should run into the same issue. But it makes me believe that we are, at LinkedIn, we are really like composing the most sophisticated portable pipeline for Bing. And that's pretty cool. So that's pretty much it about the use cases. If you have more questions, you can come to me after talk. In the final 2 slides, I just want to quickly mention future work. So we are working on the young cluster support for portable runner. We don't support stateful Pardue yet. That's the next thing we want to do. We want to do Jupyter Notebook. I noticed that there's an iBing effort in open source, which is pretty cool. We want to do that. And Golang support as well. And for Samza runner in general, we actually plan to use Bing SQL for Samza runner. And also schema aware. All of these nice features from Bing open source. Like I said, this has been a great success to integrate Samza with Bing, and we are still leveraging all the effort from the open source community. So thank you for that. With that, that's pretty much my talk. Here's my contact information. Find me on LinkedIn or send me an email. Yeah, thank you. Oh, question?
Yeah,
Sorry, question.